idea. Look at Pn cross Pn dual. So Pn dual consists of hyperplanes in Pn, and this therefore contains an incidence locus, which is the collection of all P comma H, where P belongs to H. Or if you want to do everything in terms of coordinates, suppose xi's are the coordinates here and yi's are the coordinates here, then I is defined as the zero locus of sigma xi yi. Okay. So it's a divisor, and it is linearly equivalent to the divisor Pn cross Pn dual 1 1. Okay, the line bundle which is one from each side, and therefore it is ample, and that means that Pn cross Pn dual minus I is affine. So this is point number 1, or A. And B is that if you look at so let's call this something J of Pn. Then look at the map from J of Pn to Pn. The fibers consists of fiber at each point is all hyperplanes containing that point, and then we have all hyperplanes, yeah, and then we are removing the hyperplanes which contain the point. So Pn, the fiber is Pn dual minus so it's just a linear subspace given by sigma xi equal to 1. Okay. Sigma xi equal to 1 is an affine space, so you can think of it that way. So these are the two properties, that the fiber is this, and in fact even Zariski locally pi inverse of, let me call this pi inverse of u is locally for sufficiently small u it's an affine bundle. So now what are we going to do? We are going to take any x. Suppose x is a closed subvariety of P. Right? Then what can you say about inverse image? Is a closed subvariety of an affine space. J of Pn, and therefore it is affine. Okay. And the natural map from pi inverse x to x is an AN bundle. Okay. Which means that the topology of x is the topology of pi inverse of x. So this induces isomorphism. Tell me if I on homology and topology. Homology, cohomology, homotopy, everything. So this is the basic idea of joint loop, but we are going to extend it a little bit because we need to work with pairs. Okay, it's not just enough to work with a single variety, but we want to work with a pair of varieties. So, so now what will you do if you have x comma y, and what I want to do is to somehow replace this by something which is so. So the first step is y. So before you go to x comma y, let's take the case where x is quasi-projective. So this was case 1, x is closed. Case 2, x is quasi-projective. So maybe there's a complement which is so. So it may not be affine, affine or projective. It may be something like a2 minus a point or something, right? So, so certainly you can embed x inside some x bar, and by blowing up the complement, you can assume that x bar minus x is a divisor. Right? So you can replace x by x bar, and now for x bar we have already done the construction. So let's call this as j of x in each case. Then j of x bar contains pi inverse of x, and the complement supports a Cartier divisor. Jx is affine. Okay, and pi inverse x complement supports a Cartier divisor. Is a Cartier divisor. That means it's the zeros of the section of some line bundle. Okay. So take that. This is affine, so this is sitting inside some projective variety, some big projective variety. We don't care, right? And there the complement is an ample divisor, right? If you've got an affine variety sitting inside the projective variety, the complement can be assumed to be an ample divisor to take a completion. So you got an ample divisor, you got some other divisor, you can combine the two and you get an ample divisor. So that means the complement, that means pi inverse A is the complement of in a projective variety of an ample divisor. So it is affine. So I'm just saying an assertion which you can find in Hartshorne, for example. Okay, I hope, if not in Hartshorne, in some suitable book on algebraic geometry, which is that if you have an affine variety, then you take the complement of a Cartier divisor, the zeros of a line bundle, then that is an affine variety. Okay. Note that you have to be a little careful because it may not be an affine open set in the sense of it might not be inversion of one single function. It may be that the complement is not defined by a single function. Okay, because it's a section of a line bundle. That line bundle need not be O. Okay, so it takes a little. That is why I'm giving this slightly complicated argument. So I need a little bit of work to justify this, but it's true. Okay, so take a affine variety, take the complement of a Cartier of the zeros of a line bundle. That's also affine. So this is also affine, and so I can call it j of x. So it's affine. Okay. So now for a quasi-projective variety, we have got an affine variety. Okay. Now what do we do for a pair? Is it okay so far? I mean these things you'll have to find some book to check it. I mean I can't go over all, but basic fact which is being used here is that if you take a line bundle and take an ample divisor and then combine the two, suitably take a high multiple of that. So if you have a line bundle and an ample line bundle, and you take a very high power of a line bundle, then this ample. Okay, this is the basic fact which I'm using. Oops, why is it not working? So this is what I'm using. This is what is required. Okay. So M sufficiently large. Okay, so now next we have to look at the situation where we are looking at something like x comma y, right? Where y is, oops, where y is a sub of x, but need not necessarily be closed. Okay, we are not assuming y is closed, we are just assuming variety of x, sub of x. Okay, one thing is, I should have maybe said that right in the beginning. You may as well assume everything is reduced. I mean, it doesn't matter. We are only doing topology, and nilpotents don't make any difference to the kind of singular ordinary topology which you're doing. So it's not important. So now what you can do is, of course, your x, you can form your j of y, no problem. Now the problem is that y is not no, sorry, what did I want to do? J of y I didn't want to take, maybe.
In previous page.
Yeah.
You take L equator and T is an ample invertible sheaf.
T is an bundle, L is an invertible sheaf.
Yeah. So L tensor T is always ample. Do you want to say very ample?
No, L density is not always ample.
But the definition of ample is for every coherent sheaf, F tensor A to the power m is generated by global section.
That's right. For M sufficiently large. Yeah, that's
generated
correct.
by global section. Then it is said to be ample.
No. It is not just generated by global section. It is very ample, in fact. Here you could have put very also.
For some higher M, it will be very ample, but it will be always ample.
No, that's not true. I mean, take something like O. Look at P1 cross P1, and look at O minus 1 comma 0 as well. O. It's not a good example here because then it doesn't have a section. So let's forget that case. I mean, you can make it have a section also. Let me not worry about that. And then you tensor with O1, 1. Then you'll get O0, 1, which is not ample. Okay. So it need not be true that just tensoring once. You have to tensor sufficiently many powers. That's the correct statement. Okay. And one can give more complicated examples. So you can take, for example, you can take surface with a minus self-intersection, -2 curve. You can take a surface, and then you need to tensor by a sufficiently high power to get rid of the minus part. Okay. Minus n curve or something like that. So you have to be a little, yeah, so you can take, yeah, you can take what is called the Hirzebruch surface, F2. And there's a -2 curve in that. And if you just tensor, you have to tensor with a high enough power. But anyway, we don't care. I mean, the point is actually the only point I think it's worth remarking. All this high power and all is only to prove that it is affine. Whatever we have is already affine. We don't have to change the construction. Okay. It's just to prove that something is affine. So my only point is that if you take a affine variety and you remove the complement of a Cartier divisor, that may not be the localization of the set of points where a certain function is non-zero. A global function is non-zero. Otherwise, of course, you know that if I take spec A and spec A localized at F, that is always affine, of course. But this may not be of the form spec A localized at F. So therefore, some little work is required. just to check that it's affine. That's all. So it is spec B for some other B, but B is not necessarily of the form A localized at F. Okay. So maybe here I shouldn't write pi. I should just say pi inverse y contained in Jx. So again, you have an affine variety. So you may as well assume that y is an affine variety. Okay. And so you can assume, in other words, sorry, not y. X is an affine variety and y is a sub variety. But I don't know necessarily that it is closed. Okay. What will I do? I can whatever is the construction I had, I can apply it to y and right. So I can produce J of y, which is affine, and then J of y do the so whatever construction you could have assumed that this is happening via so I don't know how to say this x itself you embed in projective space, right, and do the construction for J of y. So J of y is affine. J of x may not be. We don't know whether it's affine or not. Well, actually it is. So you can assume x and y are affine. Maybe that's all I'm saying. Okay. But y may not be closed in x. That's the only catch that we have. Okay. But since it's affine, you can embed it in as a closed subvariety of affine space for some n. And then I can think of J of y as sitting inside J of x cross this affine space. Now it's closed because J of y sitting inside an is closed. So J of y sitting inside Jx cross an is closed. Okay. If it's closed in one factor, that means it's closed. So this means that this map is a closed embedding, and this again has the same topology as x. Because Jx has the same topology as x, so Jx cross an has the same topology as x. So we have replaced this pair xy has been replaced by another pair where Jx cross an cross Jy, right? Where there is a map, of course. Okay. Where this pair has the same topology as the original space, and this is both these are affine now. Mainak has some doubt. Meaning that in singular cohomology or any other form of topology cohomology which you look at in the sense of topological spaces, you will get the same value as for x. Okay. So I'm not writing all the arrows. There is a map. I mean here, yeah, Jx cross an to Jx there is a map, and then to x there is a map, and the whole thing is an affine bundle, and therefore nothing is changing. The singular cohomology and singular cohomology, everything is going to be the same. That's the point. So it's homotopic, whatever. It's a homotopy equivalence. This vertical map is a homotopy equivalence. Okay, even in the sense of Voivodsky, because everything is actually locally an affine bundle. It's an AN bundle. So Voivodsky would invert anything which is locally an AN bundle. Right? So even in the sense of Voivodsky's category, where he inverts AN, basically x and x to x cross to x is inverted. Is considered an isomorphism in Voivodsky's category of motives. So this gives you a okay. So given any pair, we can replace it by such a construction. Of course, we want to do actually more, right? We want to do this for the diagrams. So we are going to take. So the basic idea which I'm going to talk about today, well, this first trick is to replace diagrams. I mean, our diagram consists of corners, vertices which look like x, y, n, right? I'm going to replace this by some x prime, y prime n is unchanged, such that, I mean, there'll be a map, right? X prime, Y prime to XY, which is a homotopy equivalence. Actually, in fact, not just homotopy equivalence, this is essentially is a bundle of ANs, AN bundle in each, over each thing. I mean, it's not the same AN here. You can see that it's not the same AN for X and Y, but in both ones are AN bundles. So it's a homotopy equivalence. And what did I want? And X prime, Y prime, X prime is affine and Y prime is a closed subscheme. Okay. So we want to do this. So far we have done this, but we want to do this along with morphisms, right? So we want to suppose so we had two types of morphisms, one associated X, Y, Z, X containing Y containing Z. Now, whatever I did here with X and Y, you start with Y and Z, do it for Y and Z, and then you do it. So this case, you can easily replace by the above calculation. Now you just do it in two steps, whatever I did here, right? Whatever I did here, you can just do it in two steps, do Y and Z, and then do X and Y. Okay. So that is easy, but the other one is a little more complicated, where I have a map X, Y, let's say to T, WT or something like that, X1, Y1, let us say. So what will you do? I mean, we want with an n, we want to give a map. So we want to forget the n, we want to somehow lift it to X prime, Y prime. And then here X1 prime, W1 prime. Okay. And such that everything is now, these are affine and this is the closed subscheme, etc. So what will you do? So basically, the idea is that you would be able to replace everything. You would be able to replace the last one, X1, W1 by affine. That's not a problem. And you can take the fiber product. Okay. So therefore, you'll have a map from X prime, or you can do the Johannalu. What the basic issue is that you don't know that X prime, Y prime are affine. You can make X1 prime, Y prime affine. The problem is, how do I make X prime, Y prime affine? Okay. So then you have to go one more step on top of that. Okay. So anyway, so I won't get into the details. You can just see the notes. Essentially the same idea, taking products and so on. It's there in the notes. So this one is a bit more tricky. So so in interest of brevity, basic idea is the same. So basic idea is to use Johannalu's trick and use this Cartier divisor complement is affine, and use the fact that if I have something which is sitting inside which is not necessarily affine, I can make it become affine by taking it inside. If I already had an affine variety, a product with an AN, and then I've got something where it's embedded as a close up variety of an affine variety. So there are three parts to this process, and altogether what you can do then is, the bottom line is that therefore you can work with tuples X, Y, N with the property that X affine and Y closed. Okay. So why do you want to do this? One reason is the next, what Nori calls basic lemma. Okay. So the statement is the following. Yeah.
Y is close to embedded in X. So if we construct, like, if we have this Y embedded in X, and if we write it as a a chain of 4-dimensional 1 embeddings. So like is embedded in X, and we can if Y is embedded in X and the difference in dimension is
1.
So by 4-dimension 1, if we do it by 4-dimension 1 chain,
right.
And then if we embed X in this Pn, so we are getting a Jx which is a phi. So since the different was it like then what the one is the work for that the dimension is one.
You're saying you can take a nested inclusion, but then you have to still see that what we are doing in terms of diagrams. I would have to think about it. Yeah, you're saying something is codimension 1, but it's not closed. The problem is that it's not closed. So what will you do? So let's take the simplest case of something like A2, and then X is A2, and Y is X-axis minus origin. Okay, already it is codimension 1, but the complement is not affine in some sense. So though, and both of them are affine, but this is not closed in that. Okay, so you have to do something in this case. So the solution which we are doing is, we are saying Y is sitting. So Y is so maybe I should say what you do in this case. It's not too hard. So you know that Y sits inside A2 in a different way, another embedding J, where it is a hyperbola, right? So I can, where Y is sitting inside as UV equal to 1. And now you take the product with that embedding. So now you'll take Y sitting inside A2 cross A2. Now it is closed. Okay, and both are affine. And it's a closed embedding. So that's the kind of construction which is involved. Okay. So you have to, because the next construction which Nori is going to give, this basic lemma, it requires Y to be closed. So that is why we need this step. Also, I mean, what we are trying to do, remember, is that ultimately we want to generate this category out of things, as I said, which are simpler. So clearly the simplest ones we can think of are where X is affine and Y is a closed number, right? So this is, well, so far the simplest. The next step will say something even simpler. Okay, so that is Nori's basic lemma. So what is the basic lemma? So what he says is, given X affine variety and W contained in X closed sub, right? There exists Y contained in X such that divisor, well, actually divisor is not stated, but by construction it's going to be, which contains W, and such that you're not adding any components of dimension. Maybe I should have said dimension n, right? Dimension is n, and W should be a closed subvariety, and dimension of Y minus W is less than n. Okay, this just means that I'm not adding all the components of, I'm not adding components of dimension n of X. Okay, so in each component of X, I'm taking out something which is the proper sub. Each irreducible component, I'm taking out something, a divisor, which is a proper sub. Taking out meaning Y is a proper sub. And now with this property, that Hi of Xy is the following, is 0 if I is not equal to dimension of X, is not equal to n, and is free module free Z module, finitely generated, of course, free Z, free abelian group, where should I say, I equal to n. So the idea of this is that if you start with x, okay, then you can find this, call it x, and then there'll be an x1, which is your y, and then from x1 contains w, you can get x2 and so on, and go all the way up to xn is equal to something containing w, with xn plus 1 containing xn plus 1 equal to w. And look at the cohomology of hi of xi comma xi plus 1. Oh, this I should be different from that I. Xj comma j plus 1. This is going to be 0 if j is not equal to n minus I and is equal to free module, free abelian group, if j is equal to n minus I. Okay. And now you can use the filtered, take the chains which are supported in each xi, that will give you a filtration. So if I take the singular chain complex of x, which is x naught, contains singular chain complex of x1 and so on, right? And take the associated, this is a filtered complex, you can do the whatever is called the spectral sequence, or you can do it by bare bones, by hand method, by using bare vectors. You can see that the cohomology of x itself, x comma w, okay, hi of x comma w is the ith homology of the following complex, okay, which is what? So here you have h n minus I xi plus 1, right? And you will get a map to h n minus I plus 1 of the boundary maps in each case, xi minus 1 to xi, right? The boundary map in homology will go from, for the triple, okay, for each triple you'll get these maps, h n minus I minus 1 goes to h I minus 1 I minus 2 and so on, okay. So these are where all these are the boundary maps. Okay, this one is this one is the boundary map for this. Boundary map for this is for xi minus 1, xi minus 2. Okay, this one is for this one, and this is for this one. Right. So you'll get a complex like this, and one can show, this is some standard topology thing, is which you do when you're doing cell complexes, for example. Calculation using cell complexes is exactly the same calculation. You have replaced calculation of the cohomology of the pair by the calculation of the homology of a certain complex. And this complex consists of, in this case again, like cell complexes, consists of free abelian groups. So you've replaced, so the point is that when I think in terms of motives, what I've done is, since I've constructed an abelian category, constructed the abelian category only for such pairs which have this property. That is good enough, because that abelian category will contain the homology of all such complexes. These maps will be maps in that category, right? These boundary maps will be there even in that category, because these triples are in that category. Xi is affine, Xi is a closed subscheme, etc., etc. and all of them have that property. So in what I'm trying to say is that you make a smaller diagram than the one you started with. And even when I construct the abelian category for that, it already contains the cohomology groups which I wanted. Except that in this case, for these vertices of this diagram, the associated homology groups are all free abelian groups, which is what is going to make things much easier because we can do tensors and so on very easily. Okay. So that's this basic lemma is therefore the heart of the tensor construction. Okay. After this, the rest is again some algebra formality which I'm not going to do, which you can look at in the Nori Motives book of Muller, Stark, and Annette Huber and all. I mean, basic idea is that if I have two such pairs, x, y, and tw, I can just take the product, and it makes sense to take the homology of such a pair as the homology of the pair because there is only one cohomology group in exactly the correct dimension. There's no other cohomology. So that allows us to talk about tensor products very easily. And when you tensor, if you take tensor product abelian groups which are not free, then funny things happen. But for free abelian groups, nothing funny is happening. We know exactly what is the right thing. So in order to do tensor products, which we ultimately need, in order to talk about products and so on in our category of motives, we will be able to do that by if you make use by using the basic lemma. So the idea of the basic lemma is that we are going to replace xw, so to speak, by this complex. xw will get replaced by this complex. Okay. Now there is an issue here which is worth pointing out, that in principle there is a choice involved, right? But that doesn't matter because all we are trying to see is that the abelian category for this bigger diagram is the same as the abelian category for the smaller diagram. So in order to construct motives, I may as well have constructed the motives only for the smaller diagram consisting only of these better behaved objects. It already contains the motives for the others, right? So this is a very typical thing which we are doing. For example, even when we do when we try to construct motives for smooth projective varieties, for all varieties in Voevodsky, we often replace varieties by their resolution. Okay, so you work with the smooth varieties and then say everything else follows because of cohomology, because of theory, something happens. Okay, some quotienting, something happens. So everything is a complex there. So the basic idea is very similar here. We are trying to replace everything by something where things are easier to compute. Okay. Okay, so where was I? Yeah, so the basic, so what we want is to understand this basic lemma. Okay. So in some sense, you can see this as a way of understanding Grothendieck's theorem about the dimension of a projective variety, right? So what do we know? So what is the fundamental theorem which we know from well, either by using Grothendieck's theorem and in characteristic, since you're working with characteristic zero, we can work with Grothendieck's algebraic Derang theorem, or you can directly prove it by using topology, is that if X is affine, right, Hn of X or Hk of X is 0 for K bigger than dimension of X. So this is usually proved in the usual proof. The first proof I heard of this was using topology, is by using Morse theory, which is there in Milner's book, for example. Milner's Morse theory book, he gives a proof of this statement. But there are various other proofs. Okay, so this is the idea that it is 0 for K bigger than the dimension. So you only want to isolate the dimension, right? So how will you do that? So suppose you knew that X is X bar minus A, where X bar is smooth, right? A is also smooth divisor. Right? And now suppose I choose a B, which is also smooth, right? And maybe, yeah, also assume A is transverse intersection. Okay, so that it's also smooth or codimension. So let's take that simplest case. Then I want to say look at X, comma B minus B is sitting inside X bar minus A intersection B. Okay, maybe I'll call it, yeah. This is the same as X bar minus A, and then let's write it as B minus A, right? Because I'm just substituting. So X bar minus A is affine, B minus A is affine, and the dimension is one less, so we can write a long exact sequence. So what is the long exact sequence? H K of X bar minus A, right? And then here I have HK of I want to write the other side. Can't see. So I want to write the middle term to be this H K of X bar minus A, B minus A. Then there's a boundary map which goes to HK minus 1 of B minus A. And the previous term, so this is K, this should have been K minus 1. And then there is HK of X minus A, X bar minus A. Right? Done it correctly. Okay. So this is your long exact sequence. This is 0 for K minus 1 bigger than dimension of B, which is dimension of X minus 1. This is 0 for K bigger than dimension of X. Right? Assuming everything is smooth for the moment, we are taking you've got a smooth projective variety, you're taking two smooth divisors which meet nicely. Then X bar is that projective variety, right? And you're taking X bar minus A, and A is ample, A is smooth and ample, right? So that X bar minus A is affine. And B minus A is also affine. So it has no cohomology in bigger dimensions. It has no homology in bigger dimensions. And similarly, X bar minus A has no homology in bigger dimensions. Therefore, this intermediate one has also is 0 for K bigger than dimension X. Okay. But now I want to make a duality. Okay. So I want to do the same thing now with the dual thing, and the main idea is that there is an intersection pairing via which this is dual to H X minus B A minus B. Okay. Again, by writing, yeah. So this requires a little bit of work, but let's grant this for the moment. Okay. Then suppose I show that this is dual. Now, if I assume that B is also ample, then what happens? Then by the same reasoning, this is 0 for 2n minus k greater than dimension x, which is n, which means x is less, k is less than dimension x. So therefore, the only one where it will survive will be the middle dimension. Then it's not too hard to make it free also. Okay, so this is roughly the idea. In fact, because it's a dual, it's a perfect duality, both will have to be, since they're finitely generated abelian groups, they will have to be free. So this is roughly the idea of the basic lemma in a purely topological sense. But the problem is that the way this can be done, at least by, from what I can see, by bare hands, by using just topology, it requires Q coefficients. Okay, when the torsion business will be ultimately lost. Okay, so what is, because I think he didn't want to run into the mess of doing this by bare hands approach of topology, he used sheaf theory. So I'm not this he has written a paper in the TIFR colloquium. I think somewhere in the early 2000s there's a TIFR colloquium where Nori has written a detailed argument for this lemma using sheaf cohomology, what he calls constructible sheaves. So this is maybe, I don't know how much time. Yeah, I'm almost done. So maybe I don't have too much detail to go over in this proof about the duality. Uh, the thing is that one can get this duality theorem by replacing smooth in both cases by requiring that A is called a simple normal crossing divisor. So you get a simple normal crossing divisor, and A union B is a simple normal crossing divisor. You retain this condition of ampleness, otherwise, of course, the affine part is not required, will not happen. And then one can prove this result as it stands, but it requires some more work, because you want, in order to get this duality, basically the question is, how do you get the duality? Okay. To get the duality, you will have to work through Verdier duality, but for simple normal crossings by writing down a complex, which you normally do. You'll have to take sheaves supported on each divisor, then on each intersection, and so on. And you have to write a resolution of that type using Jacin maps and things like that. So it's a little bit messy to do it that way. It can be done, but I haven't even tried to do it today. Instead, I just said that if you want details, just look at this Nori's constructible sheaves approach, which avoids all this and does it in a sheaf theoretic way. Okay, he does it for cohomology, but then you just use the fact that cohomology is equal to homology with compact support. Okay, so that's roughly the idea, the topological idea here is this. So this theorem is what is behind it, and yeah, Nori attributes. I mean, it is called the theorem of Andreotti and Frankel, who proved it using topology. Okay, but then later proofs like Grothendieck's proof of algebraic de Rham theorem give a proof of this directly. Sizes, so maybe I should just remark that if I have an affine variety, Grothendieck's theorem is a smooth affine variety. And Grothendieck's theorem says that if I look at the complex, A goes to differential forms omega 2A, etc. Then the cohomology of this complex is the cohomology of the space. This is called Grothendieck's algebraic de Rham theorem. So maybe at some point somebody will give a talk on. with, of course, coefficients in the field, the ground field. So that shows, at least for the field coefficients, it gives the result. And actually, the field coefficient proof can also be done using Grothendieck's algebraic Dinam complex. I mean, use algebraic Dinam complex to complete the proof of this duality theorem. But then again, you'll get field coefficients. Getting it with integer coefficients seems to be a little messy. So I won't try that. So maybe I'll stop here and you can have any questions.
Other questions? Any questions from online? All right. Not then, thank the speaker.
So yeah, after claps one shouldn't speak. But anyway, one thing I wanted to remark: all this is just very sketchy. But basically, what I wanted to outline is that there is now a category of motives as envisaged by Grothendieck, and one can do some things with it. What is missing, as I said, is the vanishing theorems, and this is also true from a different point of view. So Vygotsky took a different point of view, which was formulation. So maybe somebody is going to talk about Vygotsky's work. That what he does is that he constructs a certain triangulated category, and there again one needs the vanishing theorems in order to show that that triangulated category is in fact the derived category of an abelian category. So what is missing is to find an abelian category of which it is a derived category. Okay, and of course the hope is that Nori's category is that abelian category which you're looking for. So one can try to produce functors in one direction and then try to prove that that's an isomorphism. But that proof that that's an isomorphism again will boil down to certain vanishing theorems for Chow groups, which is not known.
All right.
Yeah.
Thank you very much. Again, you make.
Sorry?
I mean, not you, but